This is chapter 17 in class exercise 2. For this in class exercise, I'm trying a different approach. So I'm not on solving them live on the video, but instead I will show you I have made a presentation which walks you through the solution in step-by-step manner, and I suggest that you work with me along with the video, so you can actually pause the video and do that particular step, and then again continue the video that will show you the next step and so on. And then I feel that that would be a better way to solve this problem, because it will give you hands-on experience of solving problem, and at the end the detailed solution is already like posted on Kodiak, so you can look at the my handwritten solution on Kodiak after you watch this video. So let's try a different approach just to break the continuity. So let's read the problem statement for first problem. There are 3 problems in this in-class exercise, and all the problems are for rectilinear translation motion only for rigid body. So the desk has weight of 75 pound and a center of mass and the center of gravity at G. Determine its initial acceleration if a man pushes it on it with a force F equal to 60 pound as shown in the figure. The coefficient of kinetic friction at A and B is 0.2. So let's look at this diagram. So this problem statement is very similar to problem statements we have seen in chapter 13, where a force is applied on the rigid body and we need to calculate the resultant acceleration of the rigid body because of these forces. So now you may be confused that how do I know whether it's the particle motion or it's rigid body motion? Well, read the problem statement carefully. In particle motion, most of the problem had the last line that neglect the size of the particle, okay, so or neglect the size of the body. That means it's particle. For rigid body, you will see the word as center of mass or center of gravity, or even graphically you will see that point G on the rigid body, and there won't be any statement in the problem that says neglect the size of the body. That means consider the size of the body. So yeah, this is the problem of rigid body. Okay, so and again the few important keywords to look into are center of mass and absence of neglecting the size of rigid body. Okay, so that is the problem statement. Very simple problem. Man pushes the table, it slides on the right, and we need to calculate the acceleration of the table as a result of these forces. Okay, so let's look into this step-by-step solution. So these 4 are the kinetic equations of motion for translation of rigid body. Well, the only thing for the translation different is this term is 0 for translation because rigid body does not have any acceleration. So sigma mg, that is sum of all the moments about body's mass center, is 0, and about any arbitrary point p is kinetic, sum of kinetic moments. So let's look into this problem. Step number 1 is you define your coordinate system. So you can say that for this problem my coordinate system is x is on right and y is going up, and you can define that positive is going right because that's the direction the table travels or the table moves, and the positive y is going up. So first step I want you to do is you can pause the video and draw a free body diagram and kinetic diagram of this problem. Indicate all the forces that you think are applicable in this situation. Now, if any force is applied at any angle, I suggest that you project the force onto x and y axis. That means you find the x and y components of the force and indicate the force as horizontal and vertical forces rather than force at an angle. For example, this force F, which is the force given by the hands of this person onto the table, is at 30 degrees with respect to horizontal line. So don't draw it like 30 degrees, but just draw horizontal and vertical components of the forces along with appropriate directions. So pause for a second, indicate all the forces that you think are applicable in this situation. Okay, so first is the horizontal component of the force that acts towards right, which is F cosine 30 degrees, vertical component of the force is F sine 30, which acts down. Then there is force, or which is the weight due to acceleration of gravity, and that acts through G. Now remember, weight always acts through center of mass. That's why it's called center of mass. Okay, so and it's mg which acts down. Now table is not in the air, it's supported on the floor. So there are support reactions at A and B. That is, these are normal forces. Normal force from ground, normal force from ground at B. Now when table slides on the ground, friction opposes this motion, and hence the direction of friction is opposite at A and B. These are the contact points at two legs of the table. So it's friction at A and friction at B, but you know that friction can be written in terms of the normal force. So I have just replaced the friction by mu n. So it's mu multiplied by this normal force, where mu k is kinetic coefficient of friction, and then it's mu multiplied by nb, which is this normal force. So that's a free body diagram. So yeah, that should be your final free body diagram. Now, what is the kinetic? How does the kinetic diagram look like? So as a result of all these forces, table will have only horizontal acceleration. So it's mass times horizontal component of the acceleration. Or in this example, you can see that this is total acceleration as well, because there is no acceleration of table in y direction. That means when person pushes the table, it slides in horizontal direction, it doesn't move up and down. And that's a kinetic diagram. So both the diagrams on one page, that's your free body diagram, this is your kinetic diagram, and these are your equations of motion. And this is our assumption that going right is positive for sigma fx, and going up is positive for sigma fy, and for moment it's counterclockwise is positive. Okay, so next step is you identify unknowns. How many unknowns do you see in this diagram, like including both the diagrams? Do we know the force? Yes, we know that force. We know the weight. Yes, we know the weight. We know the mu, but we don't know normal force. So that's one unknown. We don't know normal force at B. That's another unknown. So there are two unknowns from free body diagram, and we do not know the acceleration of the table as a result of these forces. That is third unknown. So we have three unknowns in total from free body diagram, kinetic diagram. That means we need to have three equations of motion, and we already have it. So we just need to make use of these three equations, solve for these three unknowns. So next, I suggest that you pause the video and then you actually write down sum of all the forces on left hand side. So consider all the forces and only horizontal forces that act along x direction. That means you need to consider fx, you need to consider mu na, you need to consider mu nb for sigma fx, and then that is equal to mass time horizontal acceleration, which is unknown, so you just write magx. Then next, sum of all the forces in y direction, that means you consider 1, 2, 3 and 4 forces, is equal to magy, which is 0 because table does not move up and down. And finally you write the equation of sum of moments about its mass center is ig alpha. Now table also does not rotate on its own mass center, so this term is 0. So you simply write sum of all the moments about g. That means for each force you need to consider the appropriate distance from g, and then if that moment is clockwise, then it's negative. If it is counterclockwise, and positive, and then you write down this equation. So I suggest at this stage you pause the video and you write those three equations and then proceed. And here are my equations of motion. So sum of forces in x, this is my equation. Second is this, and third is this. Well, I haven't considered here, I haven't actually expanded on sigma fx, sigma fi, and sigma mg, but you should have done that. So when you do that, you will find that you have three unknowns between three equations, and you can easily solve them because now you have same number of equations as unknown. Just do it yourself. Get the values for normal forces. Remember, the units are newtons because these are forces. Sorry, in this example pound, because I think the problem uses the FPS system. And then also calculate the acceleration, and use the appropriate unit like feet per second square, or if it is in SI system, then meter per second square. So solve this problem and then compare your solution with my solution on Kodiak. If you find it difficult, you can directly go to that solution after you watch this video and then try to solve it yourself. So, but either way, it's my sincere advice to you to solve the problem. Don't just look at the video or don't just look at the solution. You actually solve it. Do this math in your calculator and write it in your own handwriting and solve it. Okay, so that's for the first problem. Okay, next problem, 17.37. The 150 kilogram uniform crate rests on the 10 kilogram cart. Determine the maximum force P that can be applied to the handle without causing the crate to tip on the cart. Assume slipping does not occur. So this is also the problem of translation, rectilinear translation. The cart has weight of 10 kilogram. A crate is 150 kilograms. P is the applied force, and then the block, it does not slip, but it is at the. Now what happens in this situation when you apply initially, when let's say nothing is moving, that means the problem is static. At that time the acceleration of the system is 0, but when you apply the force P, and if you apply less force, then the crate stays on the cart and it moves with the cart. But then at certain point, if you apply very high force, there are chances that the crate tips on the cart. So we need to find out this maximum force at which the cart is at the verge of tipping. It hasn't tipped yet, but it is at the verge of tipping. Beyond that force, it will tip for sure. Below that force, it will not tip, but it will just stay on the block. And we need to know this maximum force because we need to optimize the operation of moving the crate. That means we want it to do as fast as possible, but we do not want to cause the tipping of the crate on the cart. Okay, so that's the problem. So let's look at this approach. So this is the problem statement. Now when force P increases, I have drawn the two forces in this diagram here in this figure. One is normal force which acts from the cart onto the crate, and the second one is friction force which holds the crate on the cart while the cart moves. So as long as this force P is less than certain value, this line of action of the normal force acts through the width of the crate. But when P increases, line of action of the force starts shifting towards right, towards the corner of the crate. As long as this normal force is still within the 0.5 meters width of the crate, it will not tip, it will just slide. It will just stay on the crate. Sorry, it slides, but it won't slide. It will just stay on the crate. So yeah, I should remove this word. We don't need it. Okay, but when this P force is more than certain value, at that time the normal force and friction force reaches its limit with respect to the size of the crate. That means this force, normal force, line of action of the force reaches at the corner of the crate. At that point, it will tip, and this is that maximum value of force at which this occurs, or this is at the verge of this situation. Okay, so we need to calculate that force P. But remember this diagram. So at the time when the tipping is about to occur, normal force reaches the corner of the crate along with the friction force meeting at that point. If you find this confusing, you studied this in statics in chapter 8, I think, for friction. So you can go back and look at the chapter 8 notes on tipping and slipping from statics. Okay, so now let's solve the problem. So first step is I suggest you draw the free body diagram of the crate and cart and indicate all the forces that are applicable. And then you also draw a kinetic diagram indicating the resultant direction of acceleration. So you can pause the video and draw the arrows like on the in-class exercise if you have printed it, or just draw the free body diagram on paper. So this is my free body diagram. So different forces that act on the crate. One of them is the weight, which is 150 kg. Actually, you need to multiply this with 9.81. So it's 150 multiplied by 9.81 through the center of mass of the crate. We do not know whether the crate is at the center of the cart, but if not, then center of mass of the cart is different from the center of mass of crate. So this arrow acts through center of mass of the cart, which is 10 kilogram. Then two normal forces on two wheels which are in contact with the ground, one applied force P, and yeah, that's it. These are all the different forces that act in the system as a whole. And as a result, the system, that is the crate plus cart, moves left with the acceleration agx. So this is the x component of the acceleration, and this is total mass, which is 150 kilogram plus 10 kilogram. Okay, so 150 plus 10 agx, and we assume that going left is positive along x for this problem, because if we do that, then we don't get any negative numbers for the acceleration. Okay. So now you apply the equation of motion for x direction only. You consider all the forces from free body diagram that acts in the x is equal to mass time acceleration from kinetic diagram, and then you get this. So sum of all the forces in x going left is positive is equal to total mass multiplied by acceleration of the entire system, where there is only one force that acts in horizontal direction, that is P. So P is equal to 150 plus 10, which is 160 multiplied by agx. And let's call this equation number 1, and we need to calculate this P only. The only thing is we don't know the acceleration, so we need to somehow calculate the acceleration, and we also need to look into that tipping condition. But that tipping occurs only for the crate and not for the cart. So what we do next is we draw a free body diagram for crate only. Okay, so this is for the box only, the free body diagram. Its weight is, again, this is 150 multiplied by 9.81, acts through its center of mass. A is the corner, and this is the free body diagram. So friction acts in the direction of motion, because when it slides or tips, the box or the crate moves right, so the friction acts left. N is the normal force at point A, and again we assume anything going left is positive, and as a result the acceleration of the crate is agx multiplied by only this time the mass of the crate, not mass of the cart, so it's 150. So that's free body diagram, this is kinetic diagram. So we need to, from this solution, from this diagrams, we are interested to know the acceleration. So we need to apply the appropriate equation of motion. So if you apply sum of forces in horizontal direction is equal to this acceleration, we don't get anything because we don't know friction as well. So if you apply sum of forces in y direction, it won't help us because there is no acceleration in y direction. If you look at the third equation, sum of moments about mass center, that is 0, again we don't get this acceleration. So we need to apply here the equation of moments about any arbitrary point A, and that equation is the one where we need to consider the kinetic moment of the resultant force, and this equation is here. So sum of moments about point A, so again for the left hand side we need to consider only one force, that is 150 multiplied by the perpendicular distance between this force and point A, which is half of 0.5, which is 0.25. So 150 multiplied by 0.25 multiplied by 9.81, because just to convert this into newtons, is equal to, so the left hand side of the equation is from free body diagram, right hand side of the equation is from kinetic diagram, which is 150 multiplied by agx multiplied by 0.5. So where 125 multiplied by EGX is just the force and 0.5 is the perpendicular distance between this force and this corner. So if you just extend this line here, this height is half of 1 meter, that is 0.5. So from this equation, we get the acceleration of the mass center, which is 4.90 meter per second square. Then you go back to this equation and substitute that acceleration here, and you can get the value of force P. When you do that, you get the value of P, which is 785. So that's what you will get from that equation 1. That means as long as the applied force is less than 785 newtons, crate will not tip. It will just stay on the cart, and then you can move the cart with that maximum force. But when the force P is equal to or greater than 785 newtons, then it will tip. So yeah, that's the solution, or that is the interpretation of the solution. Okay, third problem, problem 17.47. The snowmobile has a weight of 250 pounds centered at G1, while the rider has a weight of 150 pounds centered at G2. If the acceleration is 20 feet per second square, determine the maximum height h of G2 of the rider so that the snowmobile's front skid does not lift off the ground. Also, what are the traction, horizontal force, and normal reaction under the rear tracks at A? So let's look at the diagram. G1 is the mass center for the snowmobile, and G2 is the mass center of the rider. Okay, and we need to calculate this maximum height h that rider can have before the front skid loses the contact with the ground. Okay. So yeah, that's the question. Okay, and this is useful feature while designing the snowmobile. Okay, so let's see how to solve this problem. So step number 1, draw a free body diagram and indicate all the forces that are applicable in this situation. So first of all, the 250 pound of snowmobile acts through G1, 150 pound of rider acts through G2 straight down. Normal force at front skid. Now there is a statement in the problem which says the front skid does not lose contact with the ground. That means it's at the verge of losing contact with the ground. If that happens, then this normal force is 0. So yeah, at the verge of liftoff, this is 0. So we assume, we design it for the max worst case condition that it has liftoff. Okay, that means it's 0. Normal force at the rear track is NA, which goes up. But now the question is, what is the traction force at the rear? The force between the track and the ground, which is actually responsible for the forward motion. Okay, so that's because of the friction. What is the direction of that force? Look at A is the acceleration of snowmobile, which is on left. Do you think that the traction force acts on right because this is opposite to the direction of motion? Well, if you think it that way, then pause for a moment and let's look at the mechanism which is used in the belt in the rear track. So this is actually a belt similar to one used in tanks. So when snowmobile goes left, this track actually goes right. So when it goes forward, track goes backward where it's in contact with the ground. And that means when it goes backward, the friction acts forward, or the traction force acts forward. So this is the direction of traction force, which is, you may surprise that in the same direction of motion of the snowmobile. In fact, you should not be surprised because this is actually the force which is responsible for the forward motion of the snowmobile. Because if this force goes backward, then there is no other force which moves the snowmobile forward. Okay, so this has to go forward. So that's the resultant free body diagram. I have indicated all the forces. Under the effect of this forces, snowmobile has acceleration towards left, which is AGX, which is x component of the acceleration of, in this case, we have two different center of masses. So we need to write two arrows, like we need to draw two arrows for acceleration. one for the rider. For that you consider only the mass of the rider, which is 150 divided by 32.2. Why we need to divide it by 32.2? Because this is in pound, and when you divide it by 32.2, it's converted into slugs, and it's mass, so it has to be in slug. If it is kilogram, you can just straightforward put that value, but if it is pound, then remember to divide it by 32.2. And we need to do that same for snowmobile as well. So it's 250 divided by 32.2, it's AGX. So both the diagrams on one page, a free body diagram on the left and kinetic diagram on the right, and these are our equations of motion. Going left is positive, going up is positive for y, and going counterclockwise is positive for moment. So it's very simple now. We just need to apply these equations to solve for our unknowns. And what are our unknowns? So one of the unknown is normal force. Second unknown is the traction force. You just replace this mu na by F, which is traction force. And the third one is this height h. So we have three unknowns and we have four equations, so we can solve the problem. So when you apply the first equation, that is sum of forces in x direction, it's mass time horizontal acceleration, then you can write this equation, where for horizontal acceleration you need to consider both the same acceleration of the rider as well as the snowmobile. So Fa is the only force, which is this. Fa is the only horizontal force going left, which is positive, is equal to this is from the rider and this is from the snowmobile. And from that, because we know the acceleration in the problem, it's given 20 feet per second square, we can actually calculate total traction force, which is 248.45 pound in this example. Second thing, we need to write down equations of motion for sum of forces in y direction, and that will help you to find normal force Na. So you can pause the video and try to do it yourself and calculate Na. By the way, what is the acceleration of center of mass in y direction? It's 0, because neither rider nor snowmobile moves in y direction, they move in the x direction. Okay, so then it will help us to find out normal force, which is 400 pound, and the third one is to calculate this height h. For that we need to apply the third equation, which is this equation, where sum of moments about any arbitrary point. In this example we will select the point A, because if you select point A, then we do not have to worry about calculating moments of Na and traction force, because they will have moments 0 about point A as their line of actions pass through A. We don't have to worry about even NB, because that force itself is 0. So all we need to consider is the weight of the snowmobile, weight of the rider, and then calculate the moment about point A. This is the left hand side of the equation, and for right hand side of the equation we need to consider the resultant force on rider and on snowmobile and calculate the moment about A. Okay, and in this equation you will see h, that will be multiplied with this term. Okay, so try to write down this equation for point A of the rear track. Again, do this left hand side of the equation from free body diagram, right hand side of the equation from kinetic diagram. Okay, so when you do this, you will get this equation where only one unknown is there, which is h. We know everything else. We know the height of the center of mass of snowmobile from the ground, which is 1 foot. So you substitute everything and calculate h max, which is 3.16 feet. Okay, so that's the maximum height the rider can have before the front skid start losing the contact with the ground. Okay, because if the rider is taller than that, there is more force at the rear of the track and it will lift off from the ground. So yeah, that's a very useful calculation for the design of snowmobile, because this h will actually help to design the height of the snowmobile. Okay, so very practical example and very applicable situation.